Hello, everyone. Thank you for joining us this afternoon for our latest edition, our latest seminar in our series that is dedicated to letting early career researchers uh, in our midst give talks on their current research. Today, I'm pleased to have Kyle Broder join us from the University of Queensland. Kyle is going to be talking to us about new invariant metrics and a counterexample to the Kobayashi Wu conjecture. Thank you, Kyle.
Thanks, Tim, and thanks for the invitation to speak. Um, yeah, I'm going to talk about some recent results I got with Florian, Bertrand, and Hervé Gaussier. We've been working on this stuff for quite a while, and it's not out on the archive yet, but it will be very soon. Um, in saying that, the topic is maybe not familiar to many people, so I'm in no rush at all. So stop me any chance you can. Um, there may be a lot of assumed knowledge in here that I unfortunately have thought about various things for too long and therefore forgotten what other people might be assuming or may not be clear. So stop me at any point. So the model for what we are trying to do is essentially understand the following properties of the hyperbolic disk. So the unit disk in the complex plane has three very, well, it's got several remarkable properties, but the ones I want to mention today are the following. So the first is that every holomorphic mapping from the complex plane into the disk is constant. This is an elementary consequence of Liouville's theorem. But it also has a very nice metric on it. It's got a Poincare metric, which is or the hyperbolic metric. So this has constant negative Gauss curvature. It's bounded above by a negative constant in particular. It's also got this interesting property that the biholomorphisms of the disk, so the invertible holomorphic mappings, are isometries for this metric. And the biholomorphisms, these invertible holomorphic mappings, these form a group, which we call the automorphism group. And so what we're saying here is that the automorphism group of the disk is contained in the isometry group of the Poincare metric. And then as a
What
consequence,
does that subscript O denote in the
the
automorphism
O
group?
stands for holomorphic. Uh,
Sure, if you say so.
yeah, it's the correct reason why we say O is because of ochre, but if you see O, that means holomorphic.
Great.
Um, and then we have this other property, which is that holomorphic self-mappings from the disk are Lipschitz. So they're decreasing with respect to this Poincare metric. So understanding this picture in higher dimensions and understanding what these facts about the disk mean is really the subject of hyperbolic complex geometry. And the higher dimensional generalization of the first property, the Liouville property, is that we say that a complex manifold is Brody hyperbolic if every holomorphic mapping from C into the manifold is constant. So such examples exist in abundance, actually. So for instance, one could take any bounded domain in Cn. That would certainly be Brody hyperbolic. And this property descends to its quotients. So you could take, for instance, a ball quotient, and a very nice example of that would be a compact Riemann surface of genus at least 2. One can also find simply connected examples of Brody hyperbolic manifolds that are compact. For instance, a generic hypersurface in Pn of sufficiently large degree will give you such an example. This is attributed to far too many people for me to properly attribute it here. Uh, and one does need it to be generic in the sense that for any given degree, one can find, for instance, what's called a Fermat hypersurface, which is a hypersurface of the following form. So you just take these powers in the coordinates. You take a hypersurface of this type. sitting inside Pn, then this will have holomorphic mappings from C that aren't constant. So one does need the generic condition. And sufficiently large degree means that there exists a lower bound depending only on the dimension, such that if the degree is bigger than that, then it is hyperbolic in the sense of Brody. When understanding hyperbolicity, it's also important to understand what are not examples of hyperbolic manifolds, and the main candidates for this criterion are Cn and Pn. Should maybe note that Pn to me is always Cpn. So these are definitely non-hyperbolic manifolds. They have many holomorphic mappings from C into them. And another class of examples come from what are called Kobayashi manifolds, so Ricci flat Kähler manifolds. And so, for example, K3 surfaces and complex tori, so complex torus is the quotient of Cn by some lattice, let's say lambda is z to the n. Then these are going to, well, conjecturally they all have rational curves, or should say something more precise here. K3 surfaces have rational curves, so they have holomorphic mappings from CP1 into them, and so therefore they definitely have holomorphic maps from C into them. So they are definitely not hyperbolic, and complex tori have an abundance of holomorphic maps from C coming from the universal covering. Now, if we look at a general Calabi, I make this footnote that certain Calabi-Yals that are projective and satisfy some conditions on their Hodge numbers, these are conjectured to always have rational curves and therefore are conjectured to never be Brody hyperbolic. Okay. So the criterion in terms of this metric, what this Poincaré metric is really the subject of the present
Sorry,
talk.
can I jump in 1 second?
Absolutely.
So you said that they are supposed to have rational curves. How does that relate to having curves? Because you said the definition of Brody was for holomorphic maps from the plane.
Yeah, so if I have a holomorphic mapping from CP1 into X, then I can restrict it because CP1 will be the compactification.
Of course, thanks.
So I can just restrict the rational curve and get an entire curve or a holomorphic mapping from C. But very nice question, Ramiro. Thank you. So I want to talk about these extensions of the Poincaré metric. And to do that, I need to just make sense of what I'm going to consider to be a Finsler metric. And with about 100 years of development, it turns out the right framework is actually to talk about something a little more general, which is called a Finsler pseudometric. So Finsler metrics are not fully standardized in terms of terminology in the literature. And this is what I'm going to mean. It's one of the most general, which is that a Finsler pseudometric is just a function on my tangent bundle, which is non-negative and one homogeneous in the fiber direction. So here I'll denote the base parameter, and here's my fiber parameter, and all as I demand is the following homogeneity. In particular, I don't require it to be convex. So for instance, it would be convex if I had the following. So if I took two tangent vectors, then I would have this inequality. But I'm not requiring that. And in general, the Finsler metrics or Finsler pseudometrics we will consider will not have this property. Now, an invariant Finsler pseudometric is an assignment to a complex manifold, a Finsler pseudometric, such that the automorphism group of the manifold is contained in the isometries of the Finsler metric. So we will also say that an invariant Finsler pseudometric is decreasing if holomorphic mappings are Lipschitz with respect to this. So here you can see when you write this type of criterion down, you don't want to define it on a fixed manifold. You want to kind of think of it as something like a functor, which assigns to each manifold one of these Finsler pseudometrics. And then this is describing a kind of functorial property where you're putting kind of the morphisms are Lipschitz mappings here, and holomorphic mappings are the obvious morphisms on complex manifolds. Then, supposing one has such an invariant Finsler pseudometric, one says that a complex manifold is hyperbolic if, when evaluating this kind of functorial, this invariant Finsler metric type object on that complex manifold, it's actually non-degenerate, and it's uniformly non-degenerate. So this is the kind of modern viewpoint of the subject, which is that you don't want to talk about isolated examples of manifolds with these properties. You want to talk about all of them and then prove general properties about these Finsler pseudometrics. And then it's a property of the manifold when such a Finsler metric is non-degenerate. Okay, so this is pretty abstract.
So question, this is a rude question to some extent. Why are we interested in Finsler pseudometrics?
Because they're forced upon us. No one
Okay.
wants there to be a Finsler pseudo. One would much rather a Hermitian metric or a Kähler metric or something much nicer. But it just turns out that these various notions of hyperbolicity that were discovered, which I will allude to very soon, are characterized in terms of non-degenerate Finsler metrics.
So I guess the answer is that you can't, if you want to study hyperbolic things, you need to study Finsler things.
Well, one of the points of the talk actually will be yes and no.
Alrighty.
One of the main ingredients or the main developments is actually a construction of an invariant Hermitian metric to any invariant Finsler metric. But that's coming. Okay, so we'll have a look at some examples. And these are the 4 primary examples. So one of the first to be discovered was this Carathéodory metric. And here what we do is we define for a point x in the manifold and the tangent vector xi, we take the supremum over all holomorphic mappings from x into the disk. We look at its differential, evaluate it at xi, take its norm, and take the supremum of that. So this is going to, so this looks kind of, well, it's not so unnatural, but how would one come up with it? This came actually 30 years after one had discovered the distance function associated to this. So of course we can define a distance function between 2 points P and Q by the infimum of curves connecting these 2 points. So we can, and then we take this, we can take gamma t gamma dot t dt. So usually we have this with the square root of a Riemannian metric, but we can define a similar thing for a Finsler metric, so long as it's got a sufficient amount of regularity. With this Cx, this Carathéodory metric, the associated distance function, so the Carathéodory distance, is just given by the supremum of the, so I want to take holomorphic maps from x to d, and then I just evaluate the Poincaré distance on the image. Let me write this a bit bigger. So it's given by a very simple construction. Where the f ranges from x to d. So the distance function is actually what is due to Carathéodory in the 20s, I believe, but it was Rafen who discovered that this actually comes from a Finsler metric, and that was decades later, and the formula is given by this. So the Carathéodory Finsler metric is only continuous in general. It's invariant and it's decreasing, and if we're on a bounded domain in Cn, for example, then this will be uniformly non-degenerate. And so bounded domains in Cn are examples of Carathéodory hyperbolic manifolds. But the unfortunate thing is that we're looking at holomorphic mappings from X to the disk. And if X is compact, then you have no non-constant mappings of that type. And so the Carathéodory metric on a compact complex manifold is totally degenerate. And so therefore you can never find compact examples of Carathéodory hyperbolic manifolds. This was a major issue because compact manifolds are arguably much nicer. And so the problem was rectified by Kobayashi, and he considers the dual metric in a sense. It's not dual in any precise sense, it's just kind of the arrows go the other way around. So here what you want to do is you want to look, instead of holomorphic mappings from X to the disk, you look at holomorphic mappings from the disk into the manifold. And so what we're measuring here is we're looking at holomorphic mappings from the disk with a prescribed one jet. So we're describing the point to the origin maps to X, and the derivative at the origin of this mapping is xi, but then we scale it. So it's kind of controlling the size of analytic disks into the manifold. And then we take the infimum over all such alpha of these things here. So this is worse than continuous. It's only upper semi-continuous. It's invariant and decreasing. But the nice thing is that this characterizes precisely the compact Brody hyperbolic manifolds. So if this is non-degenerate or positive and X is compact, then we have this equivalence. So Kobayashi hyperbolicity for a compact manifold is equivalent to Brody hyperbolicity. But both of these metrics are not very nice to work with in many ways because they're Finsler. Their irregularity is terrible, but they do have very nice properties. I mean, they're invariant and decreasing, and you have this characterization of Brody hyperbolicity in terms of this Kobayashi pseudometric, for instance. On the other hand, there are these other very nice invariant metrics that have been discovered. I'm not going to actually describe how to get them because the construction is a bit more involved. But one has the Bergman metric and the Kähler-Einstein metric. And for me, Kähler-Einstein is always going to be the unique Kähler-Einstein metric with negative Ricci curvature. This exists on compact manifolds satisfying a certain property, and it exists on a class of what are called pseudoconvex domains and so forth. But these are at the other end in the sense that they are not only Hermitian metrics, they are Kähler metrics, which are among the best possible Hermitian metrics one could have, and they're real analytic. So they're kind of this opposite end of the spectrum in terms of many regularity properties. And just have a footnote here, which is that many of these constructions look like they fundamentally belong to complex geometry. And one of the recent things I did with Anton Ilyashenko and Jesse Madnick was to show that one could actually extend this theory to arbitrary calibrated manifolds. So this was a rather interesting discovery. Okay, so here's a brief summary of these two extremes. And also one of the main points to the talk, which is this fundamental paradigm which exists in the field, which is this conviction that all hyperbolicity properties of a complex manifold are faithfully represented by the invariant pseudometrics on the manifold. So for instance, the degeneracy or existence of entire curves, these holomorphic mappings from C, precisely correspond to the non-degeneracy or degeneracy of this Kobayashi metric. If you have an abundance of bounded holomorphic functions, then that will probably be, that will be reflected in your Carathéodory metric. While other properties of your canonical bundle, for example, or algebraic hyperbolicity properties are encoded in this Bergman and Kähler-Einstein metric. But as I've already alluded to, the chasm between these two is rather vast. These terribly low regularity Finsler metrics, which kind of hinder you from doing a lot of Monge-Ampere theory or PDE in general. Well, these other metrics, these Bergman and Kähler-Einstein, are very nice, but they have their limits. They don't behave well under holomorphic mappings. They're not always defined. They're harder to construct, and so forth. So more invariant metrics are desired. But outside of these four, there are really only three main constructions. Two of them actually mimic the construction of this Carathéodory metric, but using plurisubharmonic and pluripotential theory. The remaining construction is due to Wu, and this is the one that we have recently clarified and extended to a significant extent. So this Wu metric was introduced by Hongxi Wu in 1993, and he discovered an invariant metric that is Hermitian but not Kähler in general. And the construction comes from convex geometry, and in particular, the correspondence between ellipsoids and symmetric matrices. So if you start with a Finsler metric and say fx, what you can do is you can take its double dual or its Boozman metric. This is kind of like it's an analog of the double dual in a Banach space. It's the same type of idea, this and then relating to reflexivity and so forth. So you can take this Boozman Finsler metric, and so the key point of doing the Boozman construction is if you start with the unit ball, which is given the fancy name of indicatrix for a Finsler metric. So this is the xi in Tx x such that fx of xi is less than 1. So this will be at a point x. Then this is not convex in general, but if you pass to the Boozman metric, it will be convex. So we can get a convex body from the indicatrix of the Boozman metric. And it turns out that there's a whole industry of producing ellipsoids associated to convex bodies. And if you have an ellipsoid, then you can construct a Hermitian metric, the correspondence given precisely by the unit ball of that Hermitian metric will be that ellipsoid. And this is sometimes called a Minkowski functional. So if I want to construct a Hermitian metric from a Finsler metric, I want to construct an ellipsoid out of the convex body associated to its indicatrix or its unit ball. And the one that Wu works with is what's called the Launer ellipsoid. So the Wu metric is in correspondence with this Launer ellipsoid. Which is the ellipsoid of minimal volume that contains the given convex body. And so let me draw some terrible picture that's probably not even convex. And then I form an ellipsoid inside this, and then I minimize this ellipsoid containing this convex body, but I minimize the volume. And then we do this at each point, and that will give a Hermitian matrix at each point. And now the point is to study the regularity properties and so forth of that Hermitian metric. A priori, there's no control at all. And it turns out that the Wu metric is not even upper semi-continuous when one works with this construction. So These also have poor regularity. But this is not so bad. I mean, we have distribution theory and currents and so forth, so one can still talk about various things. But yes, are there any questions at this point? Because this is quite a lot of theory. Okay, so this is one of the main results, one of the results of the paper, which is that one can do this in a much more general setting. It turns out that these ellipsoids come in an LP family. So there's like an LP Brun-Minkowski theory lying around. And in particular, when p equals 2, the metric can be given explicitly. And this was the actual starting point of this. So this was realized in the context of real Finsler geometry by Matviev and Trayanov in 2012. So what they did is they used this type of metric, this what they called the Binet-Legendre metric, in the context of real Finsler geometry, to reduce all these open problems in Finsler geometry to problems of the Binet-Legendre metric in Riemannian geometry, and then that was essentially already resolved. So it was just understanding what properties of the Finsler metric correlated to properties of the Binet-Legendre metric. And the starting point for this work was the fact that if you started with an invariant Finsler metric, then the Binet-Legendre metric of that would also be invariant. And so this gives you a new one. And then we later realized that the Wu metric and the Binet-Legendre metric fit into a more general LP family, with the Wu metric corresponding to p equals infinity and the Binet-Legendre metric corresponding to p equals 2. Now, some nice properties of this is if you were to start with a Hermitian metric to begin with, then this construction doesn't change anything because you already have an ellipsoid. If you are non-degenerate and continuous, then you have a continuous Hermitian metric for every p. But the main point is that for p equals 2, you have a very explicit construction. And in particular, if you were to start with a CK Finsler metric that's also convex, the latter assumption is not so troublesome because you can always pass to this Boozman construction. Then the Binet-Legendre metric is also CK. So this is very, very nice. One will not get a decreasing metric out of this, but it will be quasi-decreasing in the sense that the constant here doesn't depend on the f, it depends only on dimension. This is a very, very nice property. Okay, so one of the points of the first slide that I haven't given any attention to so far is what one generalizes this Gauss curvature being bounded above by a negative constant to. And this is given by the notion of the holomorphic curvature or the holomorphic sectional curvature. So we say that a Hermitian metric has negative holomorphic sectional curvature if the curvature tensor with xi in every argument is bounded above by a negative constant. If one has a Kähler metric, for instance, this is equivalent to restricting the sectional curvature to the two planes that are invariant under the complex structure. A very nice observation due to Wu was that this actually can be defined for arbitrary Finsler metrics. And if the Finsler metric is Hermitian, it coincides. So what one does here is if we have let's say we have a piece of our manifold, and I take a point x, and I have a given tangent direction xi, then I can look at a holomorphic mapping from the disk into my manifold, such that f of 0 maps to x and f prime of 0 is xi. I can pull back my metric to the disk. I'll get now a metric that looks something like maybe g of t dt tensor dt bar. And I can now take its Gauss curvature. And then I can take the supremum over all such holomorphic mappings, and this is precisely the holomorphic curvature of the Finsler metric. And again, if the Finsler metric is Hermitian, they're equivalent. So this has a very nice consequence because of the formula for the Gauss curvature. If I was to look at the sum of two metrics that have, so let's assume, for instance, that G and H, so G has holomorphic curvature bounded above by K1, and the holomorphic curvature of H is bounded above by minus K2, then the holomorphic sectional curvature of the sum of these metrics is bounded above by K1, K2, over K1 plus K2. So in particular, the set of Hermitian metrics with negative holomorphic curvature form a convex set. And this is actually one of the key facts to the counterexample that we'll talk about in a moment. So to relate this back to Kobayashi hyperbolicity and Brody hyperbolicity, there's an old result due to Grauert, Rexiegel, and Green-Wu, which says that if we have a complex manifold with a Finsler metric of negative holomorphic curvature, again, holomorphic negative is understood to be bounded above by a negative constant, then X is Kobayashi hyperbolic. So in particular, every holomorphic mapping from C into X is constant. The examples of manifolds with negative holomorphic curvature are given by the Carathéodory metric. So for instance, any bounded domain in Cn has a continuous Finsler metric with negative holomorphic curvature. And the Bergman metric, for instance, on a bounded symmetric domain, so a Hermitian symmetric space of non-compact type, will have negative holomorphic curvature as well. So the existence of a Hermitian metric with negative holomorphic curvature is extremely important because one such reason is that you can produce Einstein metrics on such manifolds. So there's a theorem due to Wu Yao and Tosati Yang, which says that if you have a compact Kähler manifold with a Kähler metric of negative holomorphic curvature, then you actually have a Kähler-Einstein metric. It's not the same metric, and in fact, it's a big open question to classify when they are the same. But this you cannot. It's not known how to do this for an arbitrary hyperbolic manifold at the time. So with James Stanfield a while ago, we showed that you don't need this metric that's negatively curved to be Kähler. It actually suffices to satisfy the weaker condition that it's pluriclosed. And with Frederick Campana, we showed that the converse of this result is very much false. One can produce compact Kähler-Einstein manifolds with no holomorphic mappings from P1 or Tn, but nevertheless may still have a non-constant holomorphic mapping from C. So negative holomorphic curvature is much stronger than admitting a Kähler-Einstein metric with negative Ricci, for example. Okay. So this is the Kobayashi Wu conjecture, which says that if we have a complete Kobayashi hyperbolic manifold, then there should exist a complete invariant Hermitian metric with negative holomorphic curvature. So recall the fundamental paradigm is that any hyperbolicity property of a manifold should be encoded in an invariant metric. So for example, if I have a metric of negative curvature, then it definitely should be invariant. That is one of the main aspects of this paradigm. But it predicts that just, let's say we're on a compact manifold, it predicts that if I have no holomorphic maps from C, then I should have a metric of negative holomorphic curvature. Now, first remark here is that if X is compact and I have a Hermitian metric with negative holomorphic curvature, then it will be invariant. This is because the automorphism group is finite for X compact and Kobayashi hyperbolic. And so what I can do is I can average over the automorphism group. And since the holomorphic curvature condition is negative holomorphic curvature is a convex condition, the resulting invariant metric will have negative holomorphic curvature. I mentioned before that all Carathéodory hyperbolic manifolds have a continuous metric with negative holomorphic curvature. So it's desirable to see, well, okay, I've got this natural invariant metric lying around. Can I actually produce an invariant Hermitian metric or even just a Hermitian metric from this construction? And one of the things that kind of put this problem to rest for a long time was that in 1997, Jean-Pierre Desmailly produced compact Kobayashi hyperbolic manifolds that do not have a smooth metric of negative holomorphic curvature at all. The construction is rather elaborate. Essentially, he showed that his examples are fibered. So one has a surface that is fibered by curves over a curve. So this is a compact Riemann surface of genus 2. The smooth fibers are also compact Riemann surfaces of genus bigger than or equal to 2. But then he produces a fiber that's so singular that it violates a criterion that he establishes for metrics with negative holomorphic curvature. But this doesn't say anything about the Carathéodory hyperbolic case or the non-compact case. And so for a long time, I thought, well, maybe it's just that the smoothness was a big deal. Maybe one could work with very, very singular metrics of negative curvature, and maybe those still existed. But I think we've seen the title of the talk, and it turns out that that is certainly not the case. And that's the following theorem here. So the theorem is the following. For every n bigger than or equal to 6, there is a complete hyperbolic domain in Cn, so a bounded domain in Cn, that has no invariant metric of negative holomorphic curvature. This in particular, so these are all bounded domains, so they're in particular Carathéodory hyperbolic. All of these domains have a Finsler metric of negative holomorphic curvature, but no Hermitian metric of negative holomorphic curvature. And this is completely independent of the regularity. The metric can be as singular as you like it to be. It doesn't exist on such manifolds. So the idea is actually quite simple, but you have to ask the right type of questions. So if I go back a moment, we were looking at this Binet-Legendre metric, and we computed the curvature of such a metric, and it turns out to be pretty bad. It turns out to be extremely complicated when you compute the two base derivatives of this fiber integral metric. So this indicatrix here is dependent on the base parameter. So one has a base parameter dependence there and there. And the resulting curvature expression is very unwieldy. And so after spending months staring at this calculation and trying to get anything meaningful, even testing cases where the curvature of the Finsler metric was constant, it seemed to not simplify in any reasonable capacity. So I began to ask myself how I could deduce properties of the curvature without doing any calculations at all. And so one way of doing that is that since the metrics are invariant, one can use, for instance, on homogeneous domains, one can use Schur's lemma to show that when you split it up into these summands, that your metric will have to be a scalar multiple of Bergman metrics on each of these things. So for instance, if I had a, on the bidisk, something like this, then I would have to be a product metric with scalings of the Poincare metric on each factor. Now, since the holomorphic curvature is convex, if I have a Hermitian metric with negative holomorphic curvature, that will force this metric to also be true for the Bergman metric or the Poincare metrics in this case. And so now the problem, once you realize this for this class of domains, the problem reduces to, are there homogeneous domains for which the Bergman metric doesn't have negative holomorphic curvature? And for n bigger than or equal to 6, there are such domains. So these were constructed by D. Atri some time ago. And so the construction just reduces to the examples that were found by D. Atri. This is a very nice simple result, but the consequences are quite meaningful, I think. It shows that this Binet-Legendre construction will never yield an invariant metric with negative curvature. In fact, there is no construction to yield invariant metrics of negative curvature. Not all is lost, however. One of the things about the fact that we have such an explicit expression is that we can now apply what are called scaling techniques to show that on a class of convex domains, there is very strong negative curvature properties near the boundary. And that's the last theorem that I want to talk about today, which is if we take a bounded, strongly convex domain with a smooth boundary, then there are constants A and C positive, such that for all points sufficiently close to the boundary, the bisectional curvature, which is one of the strongest curvatures in complex geometry, it's a sum of two sectional curvatures, then the bisectional curvature of the Binet-Legendre metric is negatively pinched at all points sufficiently close to the boundary. And this uses properties of the Kobayashi metric and a convergence argument. This is one of the more technical aspects of the paper, and it's the reason for it being delayed on the archive. But yeah, I think I'll stop there. Thank you.
Thanks very much, Carl. Let's all thank Carl for taking us through these interesting results. Does anyone have any comments or questions they'd like to ask of Kyle at this point? I have a slightly more elementary question, Kyle.
Let's hope I can answer it.
Well, I guess it was a couple of slides back. I guess it was the slide where you made specific reference to geometric PDE, and I thought, oh, I should pay attention to this. Yeah. So this is perhaps something that seems to happen a lot in complex geometry that I haven't seen as much in Riemannian geometry. The existence of distinguished metrics that have certain properties allow you to make conclusions about the existence of other metrics that have even nicer properties.
Yeah.
Wondered if you could elaborate on that for me.
Absolutely. That's one of the very nice aspects of complex geometry. One thing I only realized actually maybe within the last 6 months to a year is that complex geometry is much more related to PDE than, let's say, ordinary Riemannian geometry. In complex geometry, you do PDE from day one, and all these metrics come from PDEs that you learn how to get existence results from and so forth. So what is going on with this Wu-Yao theorem is that essentially you construct or consider some Monge-Ampere equation that you cook up from the geometric setting, and what you need to do is essentially get some long time, like, you want to take a continuity type method, or you want to evolve the family of Monge-Ampere equations that you have or something. So
So
typically,
you always need a good starting point.
yeah, so you typically will get something like some family of metrics omega epsilon, and then you have some Monge-Ampere equation like this. And here these omega epsilons are something like, I don't know, epsilon plus epsilon 0 with a fixed metric plus, I don't know, minus Ricci omega 0 plus a potential. That will depend on epsilon too. And then what you want to do is kind of let epsilon go to 0 or something. And so what this ends up being is actually, well, you just need uniform estimates. And the main estimate you need is typically something like trace omega epsilon with omega hat, for instance. If you can bound that from one side, then you can usually just get the other one via the Monge-Ampere equation. And this, you don't need any relation between omega hat and omega epsilon. You just need this. But what you will need, this is an estimate like this, is a very nice thing called the Schwarz lemma, which is where I put my money in a long time ago. And that's where the negative curvature condition is used. The reason why this has to be a Kähler metric or a pluriclosed metric, precisely to get this estimate here.
So is the method of continuity, is that like the most popular method that people have to study PDEs that arise in complex geometry?
The Kähler-Ricci flow is pretty good.
Oh, yeah, yep.
But there is a kind of standard machine that you plug stuff in. Once you get C2, once you get a Schwarz lemma, many times you actually get all the higher estimates for free.
Okay.
So the crux is usually in the like, I don't even need a C0 for most of my applications. It's just this C2 estimate here.
Okay. Great, thanks for that. Does anyone have any further comments or questions? All right, in that case, let's thank Carl again for taking us through these results.
Thanks for listening.
Stopping recording there.